being a reinforcement learning person, I should have thought of the idea of playing a game and actually rewarding you for something, but I will not do that. I do want, however, to talk about reinforcement learning and specifically about continual reinforcement learning, which is a way of doing reinforcement learning that I've been thinking about a lot, also with my colleagues in the last little while. So I'm going to start with a slide that was actually in my PhD defense almost 25 years ago, which tells you why I've always been inspired by reinforcement learning. It's really like life. It's about an agent that's embedded in an environment that interacts with this environment with the goal of controlling it. The environment is unknown, it's stochastic, does its own thing, and the agent still has to learn from this interaction how to achieve a set of goals. We very often think of these goals as being expressed by a reward function, which in our case is a numerical signal. But more recently, of course, with the rise of large language models, we've also started to think about other ways of expressing rewards, for example, by preferences that the environment might have over the agent's actions. So reinforcement learning is really like life. It's also led to a lot of interesting empirical successes. A lot of the early work focused on games. Go, of course, is a very on-point example, which probably everybody here knows, but also games like StarCraft, which are multiplayer, partially observable games. And on the bottom there, you see a set of games and environments applications in Android, where agents can interact with a phone, observing the image on the phone, and then touching the phone anywhere. This is a platform that my team in Montreal open sourced a few years ago. And where we can have our agents interact with a very wide variety of environments with different reward functions, different goals, but all set in the same perception and action setup. Now, reinforcement learning can also solve complex real problems. Here are two of my favorites from recent years. On that side of the screen, you see a loon balloon. This is work that was done by Mark Bellmeyer and other colleagues in Google Brain in the Montreal office a couple of years ago, published in Nature, where you have a reinforcement learning agent learning to control a balloon that flies up in the atmosphere and provides Wi-Fi coverage to remote areas. And so the idea here is we want to do this kind of control. It's very hard to control balloons because really you can just move them up and down, and so they have to figure out all the sort of currents in the atmosphere and catch the right current in order to kind of hover over an area. And so the recipe to get this to work is to take a simulation, train an agent in simulation, and then actually deploy it on a real system and let it to continue learning while it's in that real system, embedded in that real system, because if you don't continue learning, the simulation is imperfect and you're not going to figure out the current circumstances that you're in and how to do the control right in that place. But the simulation helps a lot to kind of put the agent in a good initialization. On the other side, you see an example where reinforcement learning has been applied to control fusion reactors. This was a collaboration of DeepMind and ETH, also published in Nature in 2002, where reinforcement learning agent learns to control plasma inside of a fusion reactor into a particular shape that's desired in order to produce energy. So in this particular case, there is also a simulation, but there is a real system. We need to adapt to that real system, which is, simulation is never perfect in these circumstances. And also, it's a task where we have no prior knowledge, like people don't know how to control fusion reactors. And so you really need to have learning from interaction in order to get anywhere in this kind of task. There's a lot of other examples of this sort: adaptive treatment design, drug design, of course, reinforcement learning from human feedback, where these types of algorithms have been used. One of the things that actually was always very exciting to me is that reinforcement learning is also a model for neuroscience data. And so this picture is from the early work of Schultz and Diane, looking at using the sort of core reinforcement learning algorithm, temporal difference learning, to model the activity of dopamine neurons in the brain. And after that, there was a whole line of work, Yael Niv, Nathaniel Daw, lots of people have looked at reinforcement learning as modeling different aspects of brain activity. Now, Chida's lab is doing some really interesting work extending these results from the activity of dopamine to distributional reinforcement learning, so more modern algorithms in reinforcement learning. So as a field, I feel like reinforcement learning is done very well. There's lots of engineering practice. There's different kinds of applications that have been built. Some of them quite impressive, like the ones that I showed you before. But our agents are quite inefficient, okay, especially if you think about biology. So I put here a comparison with people because we think of ourselves as being intelligent. If you think of comparisons with other animals, this becomes even more striking. So we have one lifetime. You know, if we're lucky, it's going to last about 100 years. In those 100 years, we're going to have some amount of muscle activations. We're going to have some amount of neurons firing. There is a finite amount of experience, large but finite, that we have. And from that experience, we learn lots and lots of different things. We learn to play chess. We learn to jog. We learn to go to conferences and write papers, all kinds of stuff from one stream of experience. Now, of course, we have maybe good hardware that's been set up by evolution, right? We have good priors and so on. But nonetheless, there are currently no reinforcement learning algorithms or other kind of learning algorithms for that matter that can do learning with this amount of data efficiency or with the amount of energy efficiency that we have, right? We need about 3,000 calories per day. If you think about what the inference costs in current large models, for example, it's way, way more expensive than that. So I'm quite intrigued by this sort of gap between the amount of energy and data that biological intelligence needs and the amount of energy and data that digital intelligence needs these days. And I would really like to see us bridge that gap and bring our digital agents to be more like biological agents. So thinking from a more naturalistic perspective and building on what we know from natural intelligence to understand what are the principles that allow us to do that. And so from this point of view, one of the things that I've been thinking about and sort of a way to think about why sort of natural intelligence is more efficient is that you actually have agents that are not very big. They're small. Certainly, they're much, much smaller than their environment, okay? Now, that's, you know, maybe a strange thing to say in the era of large models where it seems like we can just scale things up and up. But if you think about an agent embedded in an environment with other agents, almost by definition, this agent is small because there's lots of other agents in the environment. They do different things. You know, they may be similar in size and so on. So this agent is just a tiny drop in the bucket in a very big environment, has one lifetime, one trajectory that it's learning from, and that puts pressure on it to continually learn and adapt from the data that it sees. So we're thinking of this agent as having one stream of experience, that's observations, actions, and rewards, only time to travel on a specific trajectory. The agent cannot compute arbitrarily fast, cannot remember all the relevant information necessarily in a giant replay buffer like we normally do these days in reinforcement learning, and it has to interact with the world at its own pace, right? So the interaction is not necessarily synchronous, you know, time ticks and then the agent takes an action and time ticks again. Really, the environment is full of other agents doing things at their own time scale, and this agent is observing and acting at its own time scale, and it might in fact be able to choose the time scale at which it wants to act, do credit assignment, and learn. So that's sort of the high-level view. Now, this is not exactly like classical reinforcement learning, you know, Markov decision processes and so on that you're taught in school, but it's a natural evolution of ideas. Initially, people thought of this sort of sequential decision-making problem as being solved by dynamic programming, where you have an agent which is trying to find an optimal policy in an environment, and it's trying to act optimally in all possible situations that might arise in that environment. And in order to be able to do that, we need to rely on some structure in the environment, and the structure we've sort of hold on to very dearly is Markovian structure, because that gives us a lot of nice mathematical and algorithmic properties. Now, in reinforcement learning, the agent doesn't actually care about all the possible states, even though theory papers might make you think that. The agent really cares about the states that are encountered during its experience, right? This is one of the key ingredients in making Go work, for example. In Go, the number of states in the environment is astronomical, but most of these states are actually not encountered in real games. And so the agent actually focuses on states that are encountered in real games and really understands how to act in those specific states. So now I want to take this one step further and think about the agent learning something that should enable it to do well in the future, on the future trajectory that it's going to encounter from the current situation that it's in. And so this gives rise to a set of perhaps desirable algorithmic properties, and I'm going to show you two vignettes sort of addressing some of these algorithmic properties through sort of ideas for how to train these agents. The first and perhaps most well-studied thing is the dilemma between stability and plasticity. Stability says an agent is learned something, should be able to remember that for the future, okay? Plasticity says, oh, but the agent might actually see new things in the future and needs to maintain some capacity in its brain to learn those, okay? And so this is a dilemma because if the agent has finite capacity, it needs to decide what to retain and what to throw away in order to be able to still learn in the future. Now, there's a more nuanced version of this, which I'm going to call graceful degradation. If you have in the future a data distribution that's very similar to what you've seen in the past, then you should actually be able to do pretty well because you've had training in this data distribution. If you somehow get teleported into a completely different data distribution, then it's okay to not do very well. And so it's a more nuanced version, perhaps, of stability and plasticity. The third really important thing is scalability, right? This is sort of going back to Sutton's bitter lesson. We want our agents to be able to get better the more data that they see and the more compute that they have available. And so any kind of learning algorithm has to be able to get better with more data and more compute. And then the fourth property is something that is more debatable, but it's really dear to my heart because I have 3 kids. I'm going to call this self-reliance, okay? Self-reliance means the agent has to be able to learn and understand the world from its own stream of experience, not necessarily by being taught. If there's a teacher there and can provide useful information, great, that becomes part of the agent's stream of experience, right? But you cannot necessarily rely on something else or somebody else babysitting the agent all the time. So I'm going to start by talking a little bit about the stability-plasticity dilemma because this is actually one place where a lot of progress has been made in the field in the last couple of years. The idea here is that if you have a neural network that's inside the agent's brain, there are some links that capture useful knowledge, which we may want to retain over time. So in this picture, those are the red links. They're being retained over time. But as the agent is going through the learning stages and is seeing perhaps new tasks, different types of situations, different types of reward signals, it needs to also add to this. So there's some links that are available for training, and some of these are going to be retained at the next stage, right? Maybe those are the blue links. And some other of these links are going to be destroyed, okay? And sometimes people call this phenomenon interference. Sometimes they call it catastrophic interference, but I don't like the catastrophic word because it sort of sounds bad. And actually, I think it's okay to forget, right? It's actually quite useful to forget if you have a limited capacity agent. Now, one thing that happens with deep learning agents is that as we train them, they are sort of biased towards stability and away from plasticity. As they see more and more data, they become sort of very set in their ways and they're no longer able to learn new things. And so that happens in deep reinforcement learning agents. There was a paper by Nikishin and colleagues that was showing that. It even happens in supervised learning agents that are in continual learning settings. And there's been quite a bit of work in the last 2 years trying to understand this phenomenon and fix it, including a couple of papers there. Lyle et al. Was presented here at NeurIPS from my colleagues at DeepMind, and then Dohar et al. Is a recent Nature paper from Rich Sutton's group at University of Alberta. The ideas that are being proposed are essentially to have some amount of resetting of weights between learning stages or as the agent goes along. So if you put the weights again close to 0, then you have again capacity. So you retain some plasticity, but now you're losing some stability, and it depends how smart you are about the things that are being perturbed towards 0. So that's an algorithmic solution. It doesn't feel quite right in the sense that it's somewhat arbitrary. It's also not exactly biologically plausible, okay? And so one of the things that we've been trying to look at is what do we know from natural intelligence? Are there any solutions there that help our brains maintain plasticity while also having stable knowledge. And so this is a picture taken from this paper by Kumar and Hassabis and McClelland, which talks about complementary learning systems. Complementary learning systems means there are parts of the brain that are learning fast, that can acquire knowledge very quickly, and then over time that knowledge gets sort of processed into more stable part, and it gets retained, okay? So the fast learning is often understood to happen in the hippocampus, sort of the little red dot, the sort of area there. And then over time, that knowledge goes from the hippocampus to the prefrontal cortex and other areas of the brain and gets consolidated, okay, oftentimes through replay mechanisms or during sleep. So one thing that we try to do is to think about what would be the simplest implementation of a complementary learning system idea in a reinforcement learning agent. And so this is joint work with my PhD student, Nishant Anand. The idea that we explored here is to take the sort of bread and butter of reinforcement learning algorithms, the value function, and think about how would we modify the learning of the value function in order to have a complementary learning system set up. So the value function generally tells you how much total expected reward you think you're going to get from the current situation onward. It's usually implemented by a neural network trained by some version of temporal difference learning algorithm. So here we're going to think of the value function as having two parts, one which is permanent, okay, and one which is transient. The transient part is supposed to learn very quickly as the data comes in, okay, and also forget, while as the permanent part is the one where you consolidate the knowledge and you retain it over time. And so the real value function is a combination of these two things. We can think of lots of different ways of combining things, but the easiest thing to do is just to add them up, right? Since both of these things are providing numbers. In principle, they can have different features, okay? And in fact, probably they should have different features. We're working on that now. But in this particular work, we try to do, again, the simplest thing and think we have the same set of features, just one of the value functions is going to learn fast, the other one is going to consolidate slower, both of them using TD style updates. And so here we're looking at how this works, okay? And our agent is always going to be this sort of blue curve. Red is an agent that just uses normal temporal difference learning, so always sort of updating, and green is an agent that does resetting, so takes some amount of weights and resets them down. And here we have two different tasks. One is a sort of small grid world navigation task where it's small enough that the agent can represent it exactly. The other one is a bigger navigation task, still pretty small, but big enough that the agent is looking at the image rather than sort of remembering things exactly. And what we're showing here is value estimation error. So in this case, the agent is behaving in a fixed way. We know what the true value of that behavior is, and we're comparing our value estimates to that. And every sort of 50 episodes, we change what the reward structure is. So these sort of corners are rewarding. We're going to start with reward in the first corner, the second one, and so on. We always reset. And we're looking both at the ability of the agent to do well on the current task and the ability of the agent to still do well if we tested it on tasks that we've seen before. So there's some dotted lines up here that are all about the past tasks, and the sort of solid lines that are going down refer to the current task. And so what we see is that if we use this sort of very simple trick of permanent and transient value functions, we can actually have the overall error go down over time, not just for the task that the agent is currently seeing, where performance is matching or better the usual algorithms, but also on the other tasks. So there's some knowledge that's being retained from the rest of the task distribution. And we can also look at control. So this is one small example. It's a world called Jelly Bean that came from Tom Mitchell's group at CMU. Here you have a foraging task. You have different kinds of dots that have different kinds of rewards. And in this particular instantiation, we have green objects that give small rewards. And the blue and red objects flip. Sometimes blue is really good, sometimes red is really good, and blue is bad. And so again, we're looking here at an agent that has a permanent and a transient value function. These are sort of the blue curves here. And we're sort of looking for this agent to kind of quickly adapt to these changes. The baseline down here, the red, is just a randomly behaving agent. Okay, so that's a sort of very dumb baseline. And the green is a normal Q-learning agent that kind of is always learning over time. And so what you see is that Q-learning does suffer from loss of plasticity. So as we see more and more of these tasks, where the reward switches, it loses the ability to be able to learn, whereas our agent is always capable of learning. There's always a drop when we switch because, all of a sudden, red was really good and now red is really bad. So you need a little bit of time to gather data to understand that. The other pictures here are showing you how often we get sort of the middling rewards, the top rewards, and the bad rewards, okay? And so one thing that you can see here is that sort of the frequency of getting the middling rewards is actually very stable and higher, okay? So the agent is sort of relying on that almost in order to do well. What's happening with these negative rewards is a little bit interesting, and my theory at least about this, like why are we getting more negative rewards over time, is that actually our features in this case, remember the features are the same, are not really good enough in order for this agent to kind of remember and make this distinction very well. We're currently working on the idea of getting better features. So I've shown you one vignette where we're trying to address the sort of stability plasticity dilemma in the model-free reinforcement learning case by using value functions. Now I want to talk a little bit about model-based reinforcement learning because I think conceptually this is something that also is a very fundamental ingredient of agents that are able to learn continually. So model-based reinforcement learning takes the view that the agent is not just learning a value function and a way of behaving or a policy, but is also learning a model of how the world behaves based on different situations and different actions that are taken. So this is sort of the simplest implementation of this idea coming from this algorithm called Dyna back in 1990, where you imagine the experience of the agent being used to learn a policy and a value function sort of directly, but also being used to update a model of the environment. And this model can then be used in the agent's head, if the agent has more computation, to imagine different situations and further update its value function and its policy. So there's planning and learning that happens with the model as well as directly from the environment. And there's actually been lots of work in neuroscience that has looked at this question of whether the brain does model-based or model-free reinforcement learning or both. And basically, the answer is yes, there's both things going on. And there's lots of interesting literature, which I unfortunately don't have time to talk about, but sort of investigating when the switch between model-based and model-free happens. Now, model-based reinforcement learning has always been sort of intuitively appealing because you're using the data not just for the current behavior, but you're also using the data in order to understand the world, and that seems important. And so, unfortunately, this didn't really work very well until this paper called mu0 by colleagues at DeepMind, which looked at a way of fitting a model to the environment that doesn't try to predict everything in the environment. It actually tries to focus the predictions on what's important. If you take the view that what's important is the quality of the behavior, then you want a model that is able to correctly estimate the value function, okay? And so that's what we call a value equivalent model. So when you have data, for example, from agents playing the game of Go, you don't just try to do maximum likelihood fitting of that data, you actually try to learn a model that is going to allow you to predict the value function correctly and to predict the actions that you should be taking correctly. And so that's how these models are trained. So the model is the same, right, in terms of architecture. It's just the objective that's different. In value equivalent models, we focus on the objective of being accurate in predicting the returns. And the execution is the same. When you have a model in the agent's head, you can start that model in a particular state, for example, the state that the agent is currently in, and you can roll it forward, see where it ends up, right? And then based on that situation, you decide what's the best thing to do. Models are very useful, especially if the agent has a little bit of compute capacity that it can leverage. So it sort of helps in the case when we have more compute. And mu0, in fact, was the first sort of model-based reinforcement learning algorithm that gave similar results to model-free reinforcement learning. Before this, sort of model-free DQN type agents, actor-critic type agents were always best. Here you see these sort of curves of mu0 going up and meeting or exceeding the model-free agents. Now, value equivalent models focus on predicting the value accurately, but they still try to predict everything about the environment, right? You try to predict the next observation, right? Or maybe you try to predict the next latent state. But if you think about what you might want to do, again, from a sort of biological plausibility point of view, you might actually want to make some partial predictions, right? Just predict some aspects of the environment that are relevant for the current situation, right? So right now I'm trying to predict whether you're liking the stock or not. I'm trying to predict whether I'm going to make my flight this afternoon or not, right? I'm not really trying to predict like what's happening at home with my kids. That's sort of irrelevant for the current setup because I can't do anything about it anyway, right? And so this idea is you're making predictions about partial aspects of the environment based on partial information that is relevant for that specific prediction. So if you have a tree of many, many possible trajectories, you might have these little snippets, like I know there's a red bit here. If I have a red action bit, that's going to flip this to a blue observation bit and vice versa. And these kinds of models intuitively apply in many, many different situations, and therefore can both be learned with less data, because we can gather lots of different data in order to learn them, but also they can be used in many different scenarios. So we've been, with my student Safa Alvar, who's recently graduated, we've been exploring this idea of doing value equivalent models that predict partially, that only predict a subset of features. And to sort of do a very synthetic and in-your-face experiment, imagine that you have an agent which is in this environment. It observes the image of the environment. There's a green goal, and the agent lives in the top half, and the top half and the bottom half are just completely separated from each other. Now, in the bottom half, we have some objects that are randomly moving around. Okay, and so the agent sees the entire image of this environment, including this random motion. And we are sort of asking it to estimate value functions, okay, and to figure out what's the right thing to do. Well, an agent that wants to get to the goal as quickly as possible should just pay no attention to anything that's in the bottom half of the environment, because that's just random noise. Should really focus on just the top, okay, and make predictions only about that. And so we can phrase this in terms of the objective being the value function prediction, but also we can try to force the agent through its architecture to not really think about the likelihood of the model, right? To still use the model to predict things in the future, but not really propagate any of that information into its trunk of features, into its encoder. So the agent has two heads here, one that predicts values, one that predicts rewards and next state information. The model is able to do that, okay? But we don't use likelihood or anything else like that to sort of backpropagate into the features. The features are really paying attention to the value function alone. And what you can see here is, compared to agents that are trained by maximum likelihood, which is this sort of red curves, you have these agents that learn super quickly, and then they're really able to maintain good performance, these blue curves. And of course, this is a very synthetic experiment, but one of the reasons why we did it is that we can control it very well, and therefore look at the agent's ability to generalize over many different types of environments that all have the same kind of structure. Right, so here we have different types of objects, different sizes of grid, and we learn on one of these environments, which is the one on the top there, and then we're looking at the agent's ability to solve other kinds of environments by using its model. If you have agents, sort of like this sort of blue curve here, that are not trained in this way, they're actually really not able to maintain performance very well, but our agent is sort of always able to do this even when the goal changes over time. Now, the other interesting thing is that partial models allow us to do deeper planning, and deeper planning is very important in order to get better quality of value function. Why is this? Well, intuitively, if I have a model that's trying to predict something very complicated, there's some error in that model. When I roll it forward over time, that error accumulates. And there's no way to manage that, okay? When we have partial models, they're trying to do something simpler, right? A simpler task means usually the model has less error. When we roll it forward over time, the prediction error does not accumulate nearly as much. And so we can do this kind of picture here on the right, where the error doesn't accumulate, even if we're doing lots and lots of roll-ups and deep rollouts. Now, we've tried to do this in various larger environments. For example, this ProcGen environment, this is used for studying transfer learning. It's a synthetically generated set of games that have similar features, but they all kind of look different. And we are looking here at the ability of these models, not just to learn, but to transfer knowledge. So here we have these sort of blue bars. These are training, okay? The orange bars are testing in a different environment. And our model is the one that's farthest to your side there. And what you see is the smallest gap between training performance and testing performance. So we're able to kind of retain the right type of knowledge, the sort of the structure of this environment. Whereas other ways of doing this, either by maximum likelihood, which are the bars farthest this way, or by not doing partial predictions, but still doing value equivalent predictions, essentially doing mu0. Those are the middle bars. Those are both sort of worse in this case. And we've done some other experiments. I don't think I'm going to have time to talk about them, but essentially you can generalize this in various ways using attention mechanisms to make the models more powerful. So just to conclude, I just want to emphasize that I think it's really important for us to acknowledge that our agents, even if they're large language models and very big and growing every day, are still smaller than their environment. And that's not a bad thing. That puts pressure on the agent to find structure in its current trajectory, in its current part of state space, continually and online. I think we've been all sort of very obsessed over time with optimality and finding optimal agents. Our agents really have to be good where they are, right? Good at the tasks that are being faced with. And we need to find the right types of learning algorithms and architectures that allow them to do that. The representations that we have may need to be modular. So some of the stuff that I've been showing you is mildly modular, right? We have two different value functions, right? Or we have a model architecture that's a little bit modular. But I think in general, it's useful to think about what types of modules we would want to have. Maybe these are partial models, partial temporally extended models. Maybe these are affordances. There's lots of these concepts that we do have in our arsenal in reinforcement learning that we may be able to leverage in this context. One interesting question is, what should we actually try to predict? So right now, with the partial model work that we're doing, we're assuming that we want to do value equivalent stuff. There may be a broader perspective there. Maybe large language models have some prior knowledge about the world that can tell us what we should be predicting, right? Because there's some information about future distribution that's embedded in there. Maybe we should be looking at neuroscience, in fact, to figure out what kind of predictions are made in the brain and sort of what's sort of evolutionarily important. And from an empirical point of view, I think we should think about the appropriate environments, metrics, and baselines that we need for these continual learning agents. And I'm going to sort of conclude with this. Over time, we have gone from very simple environments, grid worlds, mountain currents, so on, to things that are more like ProcGen, maybe StarCraft, maybe Minecraft, right? We have lots of these interesting, rather large tasks now, still pretty contained, right? And we always measure rewards. And I'm guilty of this, right? I've been showing you these return curves and these performance curves. But there's much more interesting information that we could be analyzing about our agents in terms of their ability to generalize out of distribution, to transfer to new tasks, and so on. And it would be useful for us as a community to think about sort of how do we evaluate our agents in a richer way. So I'm going to conclude there. Happy to take some questions.
Hello, really great talk. Thank you. I have a broader question, so apologies if this is something that might be common to the RL field. I'm not as familiar, but if we were to take a completely biological perspective when it comes to RL learning or reinforcement learning, are there, any projects that have attempted to completely adapt the human model, which is, when an agent reaches peak stability and plasticity declines, it spawns a new agent initializes it with base knowledge, sends the new agent out into the world to learn novel things. And then the new agent, when it encounters, a situation where it assesses low confidence, it can query the elder agent.
Yeah, that's a really interesting point. So there has been some work like this. The sort of the key word is cultural transmission. There's been some work, in fact, by colleagues at DeepMind, but also others that have looked at this idea of you have some agent that's already kind of trained, and you have kind of a baby agent that comes in and tries to copy those actions in a way. There's also a lot of work done on curriculum learning and intrinsic motivation. Curriculum learning basically means, can we set up kind of a scaffold of problems where the agents are starting with something simple and then getting to something more complicated. There's been quite a bit of work on trying to understand what a good curriculum might look like. And then finally, in terms of uncertainty, which is kind of an interesting sort of question, there's quite a bit of work in the exploration side of reinforcement learning that tries to figure out what should this agent do or where should it go in order to minimize its uncertainty. The method that is most focused on uncertainty reduction is Thompson sampling, where the agent has an explicit sort of uncertainty representation in its brain. And there's been quite a bit of recent work that's trying to take those ideas and really scale them up in sort of neural nets, maintaining uncertainty with large architectures.
So basically, once you send the young agent off to college, it can still query the elder agent about how to do laundry.
Absolutely, yes. Although ideally with less and less frequency.
Okay.
Yeah, I have a question about your comments when to switch between model-based and model-free. When and why? And I would like to elaborate the context of that question with an example. I think that I don't really have a value function. I don't know whether I have a value function, or I don't know, whenever I make a decision, I don't know how to estimate that value function. I think I have an instinct, but when I make a decision, but I don't think in terms of value function.
Yeah, I don't think you have to think in terms of value functions for the value function to be there in your brain, right? So the idea, like the dopamine experiments that I showed at the very beginning, are basically saying that the activity of dopamine neurons in the brain is explained well by this formalism of having the value function and having a specific error signal that is being computed by comparing my expectation of what's going to happen at this time step with sort of what my guess and what happened at the next time step. And so we form an error that is not a supervised training signal. We don't know the ground truth of what we should have done, but we see this discrepancy between our prediction at the current time step and our prediction at the next time step, and we use that to drive the learning. So, should you be sort of conscious that you have a value function? No, that's not necessary, right? There's a lot of underlying mechanistic stuff that's happening without that. You're probably conscious that you have a policy, you have a way of doing things. That's your way of doing things. And we think of the value function as just a helper in order to compute that policy. Now, there's other ways of computing that policy. So, for example, you can do what's called model predictive control. You have a model in your head, you roll forward that model from different choices that you might have currently. You see what happens, and then you just pick based on those rollouts. No value function involved, right? Then you move to the next situation. So that's okay. It's, it requires more compute in the moment, right? You need to do inference at action time. It doesn't explain how you arrive at very reactive policies that you might already have ingrained. Right? Okay. Thank you very much.